Hello guys, I'm back. This is a video, this is going to be a rant video to a certain extent, and it's about an MIT professor to a certain extent, not so much what per se he may be teaching as much as what he is saying. If you want to know about it, or what he is doing or teaching, well, you can look it up. Just a second here and I'll give you the information. Give me a second. Okay. Anyway, you can look up the information it's in a comment. Tom made the comment. He found this guy's lecture online, and he has a link in there because I followed it and watched it. Tom from Antique Radio and TV. Look at underneath the, I believe he made it comment on my conventional current video, I believe it was. But before I start with this guy, I have a question for you, and then we're going to go through something. At the end of this video there's going to be a little trivia question for you to research. It's not important whether you answer it or not or anything else. It doesn't matter. It's just more for your own information. And in another video I'll answer it. But my question to you is simply this: can brilliant people make mistakes? And that should be a real simple answer. Yes, they can. So this is going to get a little deep. I'm not really teaching this. This is in physics, but it is to show how a mistake can be made by a very, very brilliant and very predominantly known individual. Okay, many years ago, there was a scientist who noticed something, a problem that we were having, and it led him to a theorem, a principle, and called the Heisenberg uncertainty principle. And sorry if I can't remember Heisenberg's first name, I'm sorry on that. But he was very famous and very brilliant man. Another very brilliant man did not like it. In fact, was even actually quoted a very famous quote that God does not play dice. And the main reason was he didn't quite understand it, what the principle was really talking about and where Heisenberg was coming from with it. Even though Heisenberg wrote him several letters trying to explain, it still just didn't stick. And the person who made the quote was Albert Einstein. Now what basically the principle has to do with was, at the time we were making discoveries, and Niels Bohr came out with the model of the atom, and we were working on means of understanding that and trying to understand the momentum of the electron that is, well, in Bohr's mind, orbiting the nucleus, which was just one hydrogen at one proton in the hydrogen atom. Now, to give you some little bit of thought here about this, we have our little point that is our electron. And this is not anywhere near scale. And we've got our proton here. Now, just to pick a direction arbitrarily, we'll say that it's orbiting this way. Our problem is trying to know something about this electron, or basically know the momentum. That's one of the biggest things in physics, is to understand an object, is to understand its momentum. Now, its momentum can be zero. It can be just sitting still, and that's fine. In that case, you can find its position and everything. To take this a little bit further, let's look at a few things to understand where the problem is. Okay, let's look at a microscope. And let's look at it from the standpoint of electronics. If you're working with modern electronics, you're working with surface mounted devices that are extremely small, like 0.3 millimeters by 0.4 millimeters or even smaller. So you've got very small devices, so even with a young person with good eyesight, it's very difficult to see. So these people who daily work with this use microscopes to bring it up larger. Well, how does a microscope really work? I mean, we all know about lenses and everything. We know that it has to have some lenses in there and stuff that'll magnify, but what is it magnifying? Well, it's magnifying light. So if you got this little circuit board, it's got some devices on it and stuff like this, and it's sitting there, and you put your microscope over it. Well, what are you actually seeing? Well, what you're seeing is you have to have a light source, and this light source is shining in here light, and what you're seeing is the reflected light. Well, what really is that? What is actually happening is this light can be also known as photons traveling, and these photons will hit the objects on here. Sometimes they're absorbed, and then there's a release of a photon. Sometimes they're absorbed and lost. The energy is lost. That you'll see that in dark or darker shades. But in any case, some are reflected and stuff. So various degrees of reflection, various degrees of absorption. In any case, they're bouncing off. They're coming up into the lenses and then to your eye. Now I want you to think about that for a minute. These are flying in here at the speed of light. Now granted, to a certain extent, light technically has no mass. It does have energy. And when photons hit, like electrons, they can actually impart energy into the electron and cause it to move. So they're acting like something that has mass. In any case, you're introducing energy into this board. Now, it's not a big deal, because the mass of this board and the components on the board are so large in retrospect to the photons, which are basically massless, that it doesn't bother it. The energy that they're introducing is so low that mass easily overcomes it. Now, in the most technical sense, yes, I've introduced energy in the board. I have changed it a little bit. But it is so minuscule. Now, this works great using light to a certain extent. When you want to go smaller, the photons in visible light will not give the resolution that we need. In order to go smaller, you need something that makes a smaller footprint and will give us greater resolution. So let's say you want to look at something extremely microscopic, extremely small, like a little virus or something like that. So you got this little virus like this. That thing can be so small that using a regular light microscope, a microscope that uses light, you still cannot make detail of it. You cannot see it very well. You might be able to say that there is one there, but that's about it. It's like a real blurry picture. So in order to really see it real well, we developed another type of microscope called electron microscope. And instead of having photons be our information providers that bounce off and gives us the information, we use electrons coming in here. Much smaller than a photon by quite a bit, and they do have mass, but they're almost like a point mass. They're so small that I can really get a considerable amount greater resolution, so I can amplify much more and see much more detail at a much smaller size. I'm bouncing electrons off of this, but it's not a big deal because the mass of this virus is so great compared to those electrons that's hitting it. For all practical purposes, it doesn't give me any troubles, and I can still get the information I need when I'm looking at it and be extremely accurate. Now yes, they're introducing some energy, but it's very minuscule. But what happens when the point that I want to look at is electron? Well, the smallest thing I've got to work with is electron. So I take my hydrogen atom and I throw it underneath the electron microscope. And I try looking at that electron. I want to know what it's doing. I want to know its momentum. Now what's momentum? Well, basically momentum is velocity and mass. Okay, well, we already got a knowledge of the mass, so we don't have to really look for that, but we want to know its velocity. Well, what's velocity? Well, velocity is speed and direction. It's the same thing as saying you're traveling 60 miles per hour due north. That's your velocity. I have your speed and I have your direction. If I couple that with your mass, then I have your momentum. But the only thing I can use to measure this is an electron. Something that's exactly the same size, same mass as what I'm trying to measure. That'd be like trying to determine your car's speed, its speed and direction and everything by ramming another car into it. Am I going to get any real information from that? No. I'm going to lose the direction, or I'm going to lose the speed, or I'm going to lose both. But I'm not going to get any serious information from it. It's going to be totally lost. Well, same thing happens here. I shoot electron in here and it collides with that electron. Depending on the angle it collides at and everything will determine what this guy's going to do. He may fly off this way, he may fly off this way. Either way, he's going to have so much energy introduction, he'll probably go completely away from the atom and leave just the proton there. I didn't get nothing. No information whatsoever. Now, what Heisenberg said was, in his uncertainty principle, said that I cannot find my pieces of information I need on my momentum altogether. I can find his position, but not his velocity or his direction and speed. Maybe I can find his velocity, but I can't find the position he was at. So without both of them, I don't know anything. If I don't know if something is traveling at a certain velocity, but I don't know where he started from, or at least some points along there, I can't even really truly measure the speed if I don't really. And I can't really tell what's going on with him, and I can't even tell if he's going in the right direction that he would have been originally before I'd done anything. Anytime we measure something, we either take energy from it or we add energy to it. Taking from is like using your voltmeter, and we went over this on meter loading. You take energy from the circuit. When you try to look at something, a lot of time, look at things like under the microscope or something, you add energy in. All Heisenberg was saying was basically, all he's saying is we cannot measure this point mass because we don't have the means to do it. The only means we've got is going to introduce so much energy into it that we've lost all the information. So we can never be certain where that electron is at any point in time in any absolute way. And Albert Einstein just could not grasp that. He never did. He died without not being able to grasp this idea, because I really think because it was actually a very simple idea and he was complicating it. But he came up with his famous quote that God does not play dice. Well, God doesn't play dice with the universe, basically was the full quote, meaning that you can't leave up to chance. He was thinking this was called by chance where that electron is. By chance it may be here, by chance it's here, but there's no actual overlying physics or laws or anything else that govern it. But that isn't what Heisenberg was talking about. So anyway, I took too much time on this. Let's get to what I'm really after here. I just wanted to use this as a point of showing that people can be wrong. And I'm not going to go into all the maths or anything or even figure out circuits. I'm going to show what's wrong with this, though, and leave it at that. This guy makes a circuit. Okay, and he says we got a meter over here that we'll have. We'll put V on it. And he'll call this point A and point D. And he says we have a meter here. There. We have a battery. We have a couple resistors. Real simple circuit. And he works through Kirchhoff's laws. Loop law mainly is what he was looking at. And goes through it. And talks about the voltage drop here and the voltage drop here. What they measure up, their signs, everything. And shows how that the algebraic sum adds up to 0. Fine. Great. But then he says, let's get rid of the battery. Instead of the battery, because right now we have nothing. Instead of the battery, we'll put a solenoid coil in here. We'll hook it to an AC signal, because what we want it to do, or we can hook it to a DC signal, DC source if we want, either way. But what we want to look at is what happens is that coil energizes and a magnetic field builds. Okay, I have discussed this, where if you have a moving magnetic field, a magnetic field that is increasing in size or decreasing in size, either way, as long as it's moving, and there's a wire in that path that gets cut by those flux lines from that magnetic source, as long as them flux lines are moving, because the field's building or decreasing, you will have a induced current and consequently a voltage. Alright, that's fine. And he went on and talked about, well, it's coming out of this plane, in other words, up out of the board or the paper. So if the magnetic field's in that direction, then using a basic rule, which I've talked about, you can find the direction of the current by which direction the magnetic field's moving, and that'll give you the direction of the current. It's not neither here nor there. It doesn't matter which way the current's going. It doesn't even matter which way the magnetic field's building, whether it's going up or down. I don't care. what he did was he started looking at the voltage drop here, and he looked at the voltage drop here, and he determined that they're reversed. In other words, this might read a negative voltage and this will read a positive voltage, depending on which way the meters are hooked up. And then he used that as the idea that Kirchhoff is wrong, because they will not add up to 0 if you do that. This is going to produce a certain amount of voltage. That voltage is going to be lost across these resistors. But being of certain directions here, or how the meters are actually hooked up, I see one type of voltage, I see a negative voltage drop and a positive voltage drop, and when I algebraic sum them together with my induced voltage, I don't get 0. That's wrong. That isn't what Kirchhoff said. So the biggest problem we have here is editors, I think, and somewhat people not reading original papers. These famous people like Kirchhoff and Faraday and Albert Einstein and Isaac Newton and all these people, they not only theorized their stuff, but they put it down, they wrote it down. Some of them won, recognition from them. They published their works and stuff like that. The problem you run into is some of the stuff could be fairly lengthy, and modern day textbooks, and when I say modern day, I'm saying basically 20th century into the 21st century. Basically, at least since World War II anyway. Editors have gotten where they look at the textbook and they start editing out what they feel is unuseful information and trying to shorten things up. They try to get the authors to shorten stuff up, and you end up with, you get the basic meaning of something, but you lose a lot in the translation, at least the shortening. And that happened with Kirchhoff's laws. They took something that was a 3-page document, write up on this, his law, both laws, so you can say about 1.5 pages for each one, roughly. It's actually 1 page for the current and 2 for the other. And they turned it into one sentence. One very, very short and sweet sentence. The problem with that is it doesn't go entirely in there, and it doesn't actually talk entirely what he was saying. His basic theory is, it makes no difference about if this is measured negative or this is measured positive. His assumption and his law states, in the simplest way, without shortening a whole lot, is the voltage drop on this resistor and the voltage drop on this resistor in this closed circuit, those two voltages added together, not algebraically, but looking at the voltage drops, the amount of voltage they drop, the absolute values, the voltage drop here and the voltage drop here will equal the source of voltage. Whether that source is this EMF, the magnetics, or that source is from a battery, or what, it will equal that. So then if you actually took the algebraic sum, you would get 0. And that's what he said, because it's a conservation of energy. If I actually follow out what this guy is really trying to say, I have no conservation of energy. I'm actually creating energy out of nothing. It don't work. Whatever's being produced here, say it's producing 1 volt at some instant in time, and this is dropping 1/10 and this is dropping 9/10 because of the size of the resistor, then those two have to add together to 1 volt to be a drop, a negative, a drop of the voltage of this source. Otherwise, there's no conservation of energy. So, without going any deeper in this, and I'll let you guys do your own research on this and look it up. Because I haven't looked through everything that he's done in all of his lectures. This could be a play on things talking about the conservation of energy, and maybe later lectures he comes out and says, "Ha ha, I fooled you," because he keeps talking about being non-conservative. There is no such thing truly as non-conservative fields. That was a coin termed many years ago, and it was a term coined to try to show that we can create energy. We can't. Energy is the one thing that is conserved throughout the universe. The universe today has the same amount of energy it had in the Big Bang. No energy has ever been lost, nor has it ever been created. So no matter what you're doing here, no matter how you want to play this, no matter how many different signs you want to add and make it look like it's just sleight of hand. It's all it is. This is a magic trick. These voltage drops add together will be equal to the voltage that's induced by this magnetic field. Every time. Kirchhoff is right. So anyway, that's my rant. I hope I didn't upset anybody. And Tom, I hope I didn't really embarrass you. You were the one that said I couldn't use your name. But, and I don't think that's what you was really, you just wanted to point out that someone was actually saying this. But the thing is what bothers me, and I'm hoping, and I'm going to probably research the guy even more, but if he's not moving off of this and saying it was sleight of hand later in his course, then he is taking young minds and trying to make them believe that some really big names like Kirchhoff is totally and completely wrong. I mean, he picked on Kirchhoff pretty badly in the way he talked about him, and that is wrong. Yes, there are some possible great names out there that might have some shady backgrounds, maybe. It's real easy to pick on somebody when they're dead. Not so easy when they're still alive and they can defend themselves. So you only can go by what other people say and what they write and everything. So I don't know. You have to use your own judgment. But I feel that all those people before us, those I mentioned, along with many others who were fathers of different inventions and different things that has made our world what it is today, that all these people were great people in their own rights, and we should look upon them with that respect at the very least. So anyway, that's my rant for today. This thing is one of my longest videos, and I'm sorry about that. So take it with a grain of salt. I will make another video here on something totally different subject, but another safety video, but at least, but I think we have another one of those. So anyway, until next time, thanks for watching, and don't be too upset with me. Don't beat me up too hard. That's just my opinion. Thanks again for watching.